Hi everybody, welcome back to the Crazy Bench. As we said in the last video, what we're going to focus on this time is testing the amplifier. But I really don't want to focus on the amplifier so much as I do on the tests themselves. And of course, while we do these tests, we will also be, by proxy, evaluating the performance of this amp. So if that sounds interesting to you, stay tuned, because we're going to spend some time today doing some different kinds of amplifier evaluation tests. Now the first thing I want to do is go over a new piece of software that I just got for this GW Instek MDO 2204EX. If you remember, I got this a little while back and was kind of, for the price, I was kind of blown away at what all this thing could do. MDO stands for Mixed Domain Oscilloscope. And unlike a regular oscilloscope, this one also has functions that it can work in the frequency domain as well as the time domain. In other words, this has a built-in, at least a poor man's spectrum analyzer. Now what's the limitations of something like this? Well, it's still an oscilloscope. So the input connectors are still oscilloscope inputs. They're not very low noise floor. They're not very high sensitivity at the front end here. So it can't look at ultra small signals like what you would call a traditional spectrum analyzer would do. But when we're looking in the audio spectrum of like evaluating an amplifier and looking at frequencies and distortion and so forth, it actually does a really good job. Now you may say to yourself, well, all of these new digital scopes can do that. We can just use the FFT function. And that's very true. But the difference between the FFT function of an oscilloscope and an actual spectrum analyzer is the range of frequencies and amplitudes that you can display on the screen. So they're very different. FFT is a very basic function of looking at a frequency domain, but by no means is it a perfect substitute for spectrum analyzers. So I hope that just gives you a short description of it. There's a lot more information out there, but we're not going to get into that on this. What I'm really going to look at today is a software application that's available for download for free on the GW Instek website. And I'm not being endorsed by them at all. I literally found out about this. I wanted to try one, so I purchased one with my own money, and so I'm not being endorsed on this whatsoever. So I downloaded this program called Frequency Analysis. And if you look at if we go back here and we go to the applications, these are application software packages that you can actually install on this oscilloscope. So you can see that you have a lot of different programs that you can download. So you have the no-go app, you have a digital voltmeter application, you have data logging, you have advanced filtering, you have a mask application, so you can look at like signals over a period of time. And here's the new one, which is the frequency analysis program, and it measures phase response and it measures amplitude or gain. Okay, basically what this does is it draws a Bode plot. What is a Bode plot, you might say? Well, it's a graph that represents the gain of a signal through an amplifier, through a device under test, versus the frequency being applied to that device under test. And it also shows any phase shift that may happen between the input and the output. So what good is that going to do us for a stereo amplifier, you might say? Well, what it's going to do is it's going to show if the amplifier has a flat response curve. So if we put a set amount of amplitude into the input jack, so we connect the signal generator of this device into the auxiliary input of an amplifier, for instance, and then we measure the signal coming out of the speaker terminals, let's say, you can actually see if the gain between the input and the output changes with frequency. So if there, for instance, if you have the tone controls turned off of the flat setting, you'll see that at certain frequencies the gain will change, because you have, for instance, the treble could be turned down, or the bass could be turned down or turned up. But if you set everything at flat, technically you should get the same gain across the board from 20 hertz up to 20 kilohertz without it modifying the signal, amplifying or attenuating it. It should be flat the whole way through. Another thing that should happen is whatever the phase of the signal is that goes into the amplifier, if it shifts the phase at all at the speaker terminal outputs, it'll show that. It'll also show if that phase shift changes as you change frequencies. The easiest way to describe all this is actually to put it in action and take a look, okay? Let's do that. So here's the frequency analysis program started up, and there's a couple things that it'll show here. The first thing that you'll see, and I'm looking for something to point with, here I'll just use this. The first thing you see across the top here, this is an oscilloscope. So it's actually showing channel 1 and channel 2. See, as I adjust channel 1, or channel 2 and channel 1, see? And if I go over to oscilloscope mode, there's your oscilloscope, okay? And right now, I have the signal generator coming out of the back of the MDO going into channel 1. And then I have it going through a T and connecting it also onto channel 2. So channel 1 and channel 2 are both connected to the signal generator, and therefore, if you notice, both of them are falling on top of one another, both of the signals. So you have channel 1 and channel 2 are perfectly aligned, right? And that's what it should be. Okay? Now, if I go back to the program, since these are tied together, it's going to measure the input and the output of your device under test. And right now our device under test happens to be this piece of coax cable. So there's really no active circuitry in there. And if I hit FRA run, and we'll talk more about the setup here in a minute, you can see it goes through its self-calibration process where it sets the scaling of the two channels. Then it starts sweeping the signal from 10 hertz all the way up to 30 kilohertz. That's what I have it set to right now. I'll show you how to do that in a minute. And what it does is it puts out the frequencies, then it reads them back, and then it displays it on the plot there. And this is your Bode plot. Now notice the blue trace is showing the amount of gain. Well, of course, this is a piece of wire. It doesn't have any gain whatsoever, but it also does not have any loss, or at least none that can fit in this scale right now. Of course, everything has the tiniest bit of loss, but it's so small that for all intents and purposes, it's no loss. So this is a totally linear response curve. In addition to that, the red scale over here is showing any phase change. So if this had like a reactive component, either inductive reactance or capacitive reactance in it, you would see a change in the phase, okay? What that means is the phase of this signal coming out of the signal generator and going into here is different when it gets over to the other side here. In other words, it'll lead or lag the other channel. But since this is just a straight through piece of wire, there's no phase change. So you have both of the lines falling on top of one another. Make sense? All right. So let's do our first little test. Okay. The first thing we're going to test today is our little buffer amplifier. And if you go back a few videos, I actually did a video on this buffer amp. And it has two functions. It's a straight through buffer amp, so that means it's unity gain right now the way it's set. So whatever I put into here comes out the same amplitude out here, but it separates the impedance between the two. So no matter what the impedance needs to be here and whatever load impedance here, one does not affect the other. That's the whole thing. It also prevents noise from crossing over in between the two channels, or the input and output. And then this also has a built-in pre-emphasis for the RIAA if you want to test a phono stage. We'll get into that later. And all I'm doing is channel 1, which is your input signal, is connected to the in. And you can see this cable's a little noisy. And channel 2 is connected to the output. And if I move over here, let me get you moved over here for a minute. You can see there's our input and output once again. So the amplifier, or this buffer preamp, actually has unity gain. In other words, you can see we're on the same scale for channel 1 and 2, and you can see they're falling right on top of one another. So the gain is unity gain. Whatever's at the goes into is the same amplitude as at the goes out of. Okay, let's go back to our application for a second, and you can see it right there. There's our reference. But what happens if we do our same test? Remember how flat that straight piece of wire is? Let's see what happens if we run this test now. It's first going to go and scale itself automatically, and then it's going to start doing the test. And if you notice, those two lines are not falling right on top of one another anymore, are they? What's happening? Okay, the test is done. This represents 10 hertz. This represents 30 kilohertz. You can see the scale down here. And one glitch in this software that I noticed is that it will auto scale, but it won't always auto scale it the way that you want to look at it. So they give you the option to go in here and change, scale your Bode plot, phase offset, and I'm going to set that down. I want it to set at 0, like that. So that means this middle line is 0 phase shift of the signal, okay? And you can see at the lower frequencies, that little buffer preamp does have a little bit of phase shift. It's about 2.5 degrees phase shift between the input signal and the output signal. But once it gets past that, it's pretty much flat the whole way across. And gain-wise, though, it's exactly 0 gain. In other words, it's unity gain. And if this blue line were not straight like that, that would indicate that different frequencies are being either attenuated or boosted, depending on whether the blue line goes up or down at that point. We'll look at some of that here in a minute, what that would do. Does that make sense so far? All right. So what this tells us is there is a little bit of phase shift, and that's partially because if you look at the schematic of that gain, or of that buffer preamp or buffer amplifier, you'll see that this does have some coupling capacitors in it, and you're looking at the effect of that capacitor. So we may be able to adjust that a little bit and get it to be flat at low end, but that's clear down at the 10 hertz range, and it's only shifting it a tiny little bit. And by the time you're at 20 hertz, you're down by maybe 2 degrees or 1 degree, so it's hardly anything at all. Very low scale. All right, let's do something interesting now. I've now switched the inverse RIAA adapter, or the pre-emphasis circuit, into the buffer preamp. It does two things. Number one, it puts the phono curve for phonograph stages onto the buffer preamp, and it attenuates the signal so that a line level signal is going to be the same, is going to come out at the level of a phono input. Okay, so it changes the output to match the input of a phono stage. So you notice that blue trace, how tiny it has gotten when you compare it to the input. That's by design. Now, if you remember, a proper RIAA curve is going to reduce the low frequencies and boost the high frequencies, and then it's going to do the opposite when it decodes it, so that everything comes back flat again. Okay, I hope I didn't say that backwards. If I did, I'm sure you guys will beat me up in the comments, and I deserve it. I'll put a little note in here if I have to correct myself. So let's run the test. First thing it's going to do is it's going to scale the two inputs. And look at that. So let's change our, because again it messes up your scaling. So we're going to set the phase offset. You can see it's changing the phase. We're going to change the gain offset to, there we go. And what should happen is at 20 Hertz, it should be about 20 dB down from 1 kilohertz. So 1 kilohertz is your crossover point. So let me just set that so that it crosses over at 1 kilohertz. And at 20 hertz, you should be somewhere around 20 dB down. And let's see if I can get there. Does that look like that's crossing right there? It does to me. And then at 20 kilohertz, it should be 20 dB up. So that's exactly what it's doing. And if you notice, this is not a bad looking RIAA curve. But notice during that whole process what the phase shift is doing. And that's because of all of the reactive components in there. That's because of the capacitors that are in there that are affecting this curve. So there's reactance taking place, is what that's telling you, to make these attenuations and boosts take place. I don't know if that makes sense or not, but that's an RIAA curve you're looking at of a phono stage. Or should I say the inverse of it, because what's going to happen is you're going to have the opposite of this programmed into your phono stage, and it's going to boost this signal back up 20 dB, and it's going to cut this signal at this end down, at this frequency, down 20 dB, and make it back into a flat signal, if that makes sense. Very cool. Well, I think you now have an idea of what this thing does. It's basically comparing the goes into of an amplifier to the goes out of an amplifier, or the input to the output. I'm being silly. Now what we have connected, this wire with the white stripe on it, this is the signal coming off of my 8 ohm dummy load, which is connected to the speaker terminals of the Rotel amplifier. This wire is feeding into the input of the amplifier as well, into the auxiliary input. And what we're going to do is we're going to set that generator, the amplitude, to 500 millivolts. All right. And here's a couple notes about this signal generator. It has only two load modes. One is 50 ohms and one is high impedance. And the impedance on this thing is about, I don't know, I'd have to look it up. Let me look it up real quick. Okay, I don't have the spec sheet on this amplifier, but the input impedance is fairly high. So anyway, we're going to look at, this represents a line level signal. I'm just going to set it to about 500 millivolts. Some of them are higher than that, some of them are lower than that, but that's a pretty good spot. And again, we're going to measure from, it can only go down to 20. I'm sorry, I kept saying 10 hertz. This only goes down to 20 hertz. And it's stopping at 30 kilohertz. And we can even run that up to 40 kilohertz if we like. So that's double our hearing range, right? Let me go back. And the input source, which is the reference channel, we just have it set to channel 1 here. You can even set which of the 4 channels you use. And the output source, which is going to be your speaker outs, you know, from your amp, is going into channel 2, which is down here. So we're going to do that. And now we're going to turn the amplifier up. And I'm going to run this to about 5 watts per channel, let's say. I'm running at about 5 watts per channel into the dummy load. And we're going to run the frequency analysis. Now I have all the tone controls set flat right now. So we're actually looking at the signal going into the auxiliary input of the amplifier and coming out of the speaker terminals into the dummy load of the amplifier. Now don't get afraid of this red line, because notice it's automatically scaling itself. Now that it's done, I'm going to go in and I'm going to again scale the Bode plot so that, I'm sorry, to 0. Okay, so now the center line is no phase shift at all is in this center line. And if we look at the input from 20 hertz to 40 kilohertz, look how flat that is. And we're going to, the gain offset, you're seeing about 20 dB of gain is what that's telling you from the input. And notice how flat that is. So this is a very flat amplifier, which is good. That means that the components in the amplifier are still good. We don't have to recap it or do anything like that. But we do see that after you hit somewhere around 9, 8, 7, 6, 5, 4, 3, 2, but around 3 kilohertz, it starts shifting the phase, and back here at 100 hertz, it starts shifting the phase in the other direction. Now, this is a function of this amplifier. And notice there are no tone controls in there. But you're going to find that a lot of amplifiers will do this. So let's now adjust the tone control and see what happens. Let's run our frequency once again. I have the bass control turned all the way down now. And look at the blue line now, what happens. And see what happened? So, because I have the bass control down, notice the gain of the amplifier is lower at the bass notes, but it becomes flat at the mid-range and treble. And that's what you would expect. And conversely, if I turn the treble all the way down and leave the bass and treble both down, and I rerun the test, watch what's going to happen now. Hold on, I have to reset it. And you can see, once again, the bass is low As we go higher in frequency, it's going to flatten out for a little while. And then when we get to the treble frequencies, it's going to start dropping off again. So you're going to see kind of a bell curve there. And there you go. Now if we turn the treble and the bass both all the way up, and we run the test again, okay. And you can see now you have an inverted bell curve from the tone controls once again. I now have the tone controls set to flat once again, and I have the loudness contour turned on now. So all we have is the loudness switch. What do you think it's going to do? Okay, I just realized that when I hit the record button, it turned the recording off. And when I hit the record button to turn it off, it turned it on. So I had it reversed. So I'm going to have to redo this clip. What we're going to do now is we're going to look at the loudness contour switch and how it affects the circuit. Remember how we had a real flat signal across here with the tone controls and everything set to flat. I'm now going to turn the loudness switch on, and I'm going to run the test. And I have the volume turned up to about 9 o'clock. I'll show you the volume knob here in a minute when we're done with the test. Actually, I'll just zoom you down real quick. And you can see the volume is sitting at about 3 o'clock. Okay. Or at 9 o'clock, I'm sorry. And notice what it does. At low frequencies, there's actually a boost in the gain, and then as you get higher in frequency, it flattens back out. And that's the purpose of the loudness contour. Now, what happens if I keep everything the same, and I go down here, and I do have the focus locked, so don't worry about it, and I turn the volume up to about there, and I'm getting about 5 watts out right now. So now the volume is clear over here at about 1 o'clock. I didn't change anything else, did I? Just the volume. And if I run the test again, and I make the camera a little bit straighter, there we go. Look at what's happening to your gain right now. It's staying pretty flat, isn't it? There's a little bit of boost in the bass, but for the most part, it's almost flat. And the reason for that is because the volume is turned up so loud. And the louder I turn the volume, the less influence that loudness control will have. Remember, you ever hear about a pot having a loudness tap on it? So in other words, you've seen a potentiometer with 4 pins instead of 3 pins. So you have the lower pin, the upper pin, and then the wiper. And then you'll have that 4th pin. And they call that the loudness tap. And the loudness tap is actually a connection a little way up, about 1/4 of the way up, or 1/3 of the way up, something like that, on the potentiometer itself. It's just a fixed tap. And what they do is as you rotate the wiper of the pot and it turns up, when that wiper passes that tap and goes past it, the loudness control has less and less and less effect. So as you turn the volume up, the actual loudness contour goes down and it becomes more flat. In other words, the purpose of a loudness control is to boost the low frequencies at low volumes, because your ear can't hear the bass as well at low volume. It's just an anomaly of the human ear. So that's designed to give a certain dB of gain at certain volume levels to offset the hearing loss of your ear at low frequencies, at low volumes. Pretty cool. And this gives you a graphic representation of it. Now what you're seeing on here isn't something that you have to go run out and buy one of these MDO scopes and load this software on it to have this. There is software for the computer that you can buy that will do this. And there are even little devices, and I can't remember, it's called, what is it, the Analog Discovery or something like that. There's a couple devices out there, gizmos that you can buy and plug into a USB port of your computer with software that'll do the same kind of analysis. Or you can just buy the software and either use the sound card built into your computer, or like what I have over here, just buy yourself a good audio interface. I'll turn the autofocus back on. And that's this thing right here. I'm using one of these Scarlett 2i2s, but it doesn't matter. There's a lot of different manufacturers of these. There's cheaper ones, more expensive ones, so forth. But this takes the place of your internal sound card, is what it is. Okay, so you can do that. Now the thing that I've noticed is anything that is connected to your computer can be susceptible to certain types of noise. This Scarlett one is notoriously bad, and when I use it, whenever you, for instance, when you move the mouse, or when you scroll with the scroll button on a mouse, or you click a button on the keyboard or something, you get weird little clicky sounds and things coming out of this, unless you use the actual balanced outputs. And believe it or not, I found this out, and I thought it was me, and I thought I had a defective audio interface. As it turns out, I believe Dave Jones over at EEV Blog purchased one of these recently, and he released a short little video showing it, and he had the same problem. So it made me feel so much better that it wasn't just me. So you have to watch that. A lot of computer-based sound cards are not that good, although they can be very good. So, you know, but you know, it's like anything else. The software requires setup. You have to get everything to work. The other thing, you have to be very careful when you're using computer software. You can't just feed your speaker terminals into this. You will have to have some sort of attenuation. You will have to have protection so that you don't overload your sound card and destroy it. Whereas with this MDO, it's an oscilloscope. It's designed to see signals in the volts level, you know, up to 100 volts or so. So it won't hurt anything. You know, if you put your speaker terminals right into the input of the scope will just scale itself to it, and it's happy. The other thing is, usually the input of an oscilloscope channel is relatively low noise, so, and you won't have any of that kind of interference or anything. So it's a trade-off like anything else, but I was very impressed by what all this little thing can do. It's not the most high-end piece of equipment. I mean, obviously Tektronix is kind of one of the pioneers of the mixed domain oscilloscope, and if you want to spend $30,000 to $50,000 US on a scope, you can't beat them. They're fantastic. But you know, for what one of these costs, and you can look this up on Amazon yourself, what the MDO 2204 costs, it is a totally tiny fraction of what, for instance, the Tektronix would cost. And if you're not doing laboratory grade testing and so forth, and you don't need the input of an actual spectrum analyzer, the low noise floor and all that, this is very serviceable for the hobbyist. And it's got 2 signal generators, it's got applications like this that you can load, it's got a built-in spectrum analyzer, it can also do the FFT if you want. It really does it's in everything. It has inputs for the digital voltmeter, which you can go and put that on. You hit option, DMM on, and you can set it for, you know, AC volts or DC volts. Okay, so now you got your voltmeter on there. I mean, it's pretty cool what all this thing can do. So I'm really impressed with it. And again, this is not a review of this thing. This is just, I was really interested in the frequency analysis program. And we see it worked really well. Now, one of the other things about this scope that I don't like is all of these things, the options, you know, the settings of these options. You notice there is a spectrum analyzer and you can look at it. And we'll get more in that another day maybe. And you can't save the setup. So for instance, if I wanted to save the setup for that application, the frequency analysis, or I wanted to save a math function, for instance, like I have this math function, I can go in here and I can do advanced math and I can write a variable, or write an expression. You cannot save that expression. It just won't do it. And I wrote to GW Instek and they gave me really good tech support and got back to me, and they basically said, no, at this time we can't do that. It won't do that. And I do have the latest firmware and everything. But just some things in case you decide that you want to look into owning one of these, be aware of that. Some of the saved settings, you're going to have to fat finger all those things in every single time you want to use them. Alright, now if you recall on many of my other videos that I did in the past, I would do a frequency sweep, right? Where you would start at 20 Hertz and you'd sweep up to 20 kilohertz, and you would monitor the speaker output, and you would make sure that the amplitude doesn't shrink or grow during that frequency sweep. So checking for linearity in an amplifier, you really don't need a frequency analysis program to do that. But what it will not show you is how it changes the phase of the input versus output signal dependent upon frequency. So we saw that it didn't change the amplitude, but it did in fact change the phase at low frequencies and at high frequencies. And in the middle range of our hearing range, it was unity. It didn't change the phase whatsoever. So the frequency analysis does give you that one extra function that you can check. But to look at just for flat amplitude, you can do that frequency sweep, and I'll show you because we've done it on every other video. So we'll do one on the old Tektronix. We'll get old Reliable out here. And again, this one lets you save advanced math. So I can do advanced math on this and I can call it back up, and this thing will actually directly read how many watts you're putting out into an 8 ohm load, which I really like. You can do that on the Instek scope as well, but the problem with it is it won't let you save that math expression. So let me set up for this and we'll be right back. Okay, we're doing our frequency sweep, and you can see that I have the amplitude set to stay right between these two sets of graticules here and here. And notice that it's staying very flat. In other words, as the frequency is going up, the amplitude is staying the same. So we can do a linearity test here. That's what we're doing right now. We're starting at 10 Hertz and sweeping up to 20 kilohertz. And if you notice, it's staying nice and flat. So the amplifier is very flat. But what you cannot see with this is how it is shifting the phase at the speakers with respect to the input terminals of the amplifier. And of course, if you have phase shift at different frequencies like that, at a single frequency it doesn't matter, but if you're listening to a complex waveform like music and it's shifting the phase of the bass notes with respect to the mid-range, that could theoretically cause a little bit of distortion. All right, so you want the phase to be as flat as possible, but you're going to find in reality most amplifiers do not do that, because anytime you have capacitors and inductors and things like that, reactive components in an amplifier, they are going to affect the phase somewhat. And remember, we're looking at voltage, we're not looking at current. I mean, that's what an oscilloscope does. It looks at voltage amplitude. So whenever you see the phase shifting one way, you're looking at how it's shifting the voltage with respect to the current. So there's how we used to do, or how we normally do, our linearity analysis. Okay, does that make sense? You can see we're running, actually this is off by a factor of 10. I'm running about 10 watts per channel right now, roughly. So I don't have the scale set properly on the on the dummy load. Okay, we're now going to do something that we're first going to look at a square wave. Square waves can tell you a lot of things, because the amplifier has to be very fast in order to properly represent a square wave, especially in the 1 kilohertz range or so. And the lower the frequency, of course, the more critical that becomes. So like if I move this down, and some amplifiers really hate square waves. You can damage the amplifier if you put very high power. Again, I'm only running maybe 2 or 3 watts per channel, just a little bit of power in there. And right now I'm at 500 hertz. And you can see the rising and falling edge of this is pretty straight, which is good. And notice there's no ringing. Now let's simulate what would happen if we had a crossover in there. Because notice, if you remember, crossovers have inductors and capacitors in them. So let's take a 1 microfarad film capacitor and put it across the speaker terminals, and you can see what happens. You get this ringing at the beginning, but notice how quickly that ringing squelches out. So again, this is a very well designed amplifier. And again, we're using a 1 microfarad capacitor. That's pretty hefty. I mean, a lot of the people will test this at only, nanofarads, but it does a really good job of squelching that out. Okay, last thing we're going to do now is we're going to do a distortion test. I'm going to show you on the scope what we're going to do. We're going to drive the power up, and we're going to do a couple of different levels. So first of all, we'll go up to about here, which is roughly 10 to 15 watts per channel, something like that. 14.4. And I'm just going by the detents on the amplifier here. So we're going to do that, and we're going to look at the harmonic distortion. And then we're going to go somewhere around 50 or 60 watts per channel, which is right about here. That's 60 watts per channel. And then we're going to go to about 108 watts per channel. I believe it's going to be somewhere in the 100. Yeah, 110. There's your 110 watts per channel right there. So we're going to look at those 3 levels and see where our total harmonic distortion is. Now, the first thing we'll use is the actual distortion meter. And I have this set to look out to the 5th harmonic, and it's adding them together. So it's not just looking at the 2nd, 3rd, and 4th, the 2nd harmonic. It is actually looking at 2nd, 3rd, 4th, and 5th, and all of those combined. So here we go. We're going to do our 14 watts per channel. And you can see right there, it's pretty good. I mean, look, 0.02% THD. And we're going to go up to about 60. And you can see it climbs up pretty substantially at 60 watts per channel. It's now 0.1%, which for this amp I think is high. And then we'll go to the 110 watts per channel, and you can see it goes even higher. Now 0.3% to me for this amplifier is, I don't think is very good. So let's look at our spectrum analyzer. Okay, the first thing we're going to use is this HP 3580. This is kind of the gold standard for looking at harmonics. And if you look at it, I'm at the 10 watts per channel, or the 14 watts per channel right now. And here's your fundamental, here's your second harmonic. And you can see how low it is. And there are no other harmonics. So extremely low distortion. If we go up to our 60 watts, you can see we now have something here, and we have our second harmonic is much higher. Now we have a third harmonic, and then you have some other little, so you can see that's where that 0.1 something % is coming from. And if I run this up to the 108 watts, you can see there's quite a bit in here. We'll do one more sweep. And you can see there's quite a bit of distortion showing up. Multiple harmonics. So I don't think that's correct for this amplifier. I don't think it should do that within its power band like that, because this is rated at 110 watts per channel at a much lower distortion than that. But I want to continue on. I want to use this other test equipment first of all, because really dealing with that is a different video altogether. Just for the fun of it, I switched the distortion meter to the other channel. So now instead of looking at, I believe it was the left channel, we're now looking at the right channel. And I found something pretty interesting here. So of course we go up to our 10 watts again, or our 14 watts, whatever that is. And you can see it's even, the THD is even lower. But curiously, when I get to that 60 some watts, I'm actually right now at 60 watts per channel. Look at that. That's half what the other channel should displayed at this level. And when I drive this thing almost into clipping, I'm now running this thing at over 100 watts per channel, 100 and some watts per channel. I'm only getting, again, about half of what the other channel was displaying. So obviously there are some components on the one channel that definitely can use replacing. And again, I did not recap any of the tone control, line stage, preamp, anything like that. We only changed capacitors in the main power amplifier modules, and we changed capacitors in the power supply underneath. It was really just a small handful of caps, and they really weren't audio path capacitors. Now, there are multiple instances of those orange low leakage caps. Now, I've seen some of them. Now, the ones that were in the power modules read perfectly. Actually, they had slightly better specs than the brand new low leakage KL series that I put in there. But that doesn't mean that all of them are like that. So we're gonna do another little experiment, and I'll show you here in a minute what it is. Okay, what I've done is I've unplugged the signal generator from the auxiliary input jacks, and I plugged it into the main amplifier input jacks here. And I've separated the preamp section from the power amp section by flipping this little switch. Now, you've seen this on the Pioneer and Marantz and everything. A lot of times they just have a jumper, like a horseshoe shaped jumper that jumpers the input from the output, and you pull the jumper out to separate the amplifier. But this one actually has a switch. So what we're going to do now is I've set the signal generator to such a level that I can get about 65 watts, 60 watts per channel. And we're going to see if the distortion between the two channels changes now. So if I turn this on, you can see the distortion is still pretty respectable. And this thing's running, like I said, at about 64 watts per channel. And it's still at 0.1. That's still a little bit high, but it's better than the other channel was. So now we're going to switch channels. I'm now going to connect this to the other channel and compare. Okay, I've now switched the meter to the other channel, and when I turn it on, same power, and you can see it's very, very similar characteristic to the other channel. It's definitely not real high. And if I overdrive the amplifier a little more, it does go up. But this one, and now I'm way into clipping now, so I would imagine. But I'm right on the edge of clipping right now, and it's about still under 0.2. We're right at 0.2, which still isn't what I would expect out of this amp, but not bad. And we can do some final tweaks to the bias and offset to maybe straighten that out even a little bit more. I don't know. We'll look into that too. But the point that I'm making is it looks like we need to go back into the circuit, and we're now going to connect the signal generator to the preamp, and we're going to measure the distortion from the preamp output. So we're going to go signal generator into the auxiliary in, and then this is going to go into the preamp out. Okay, I printed out the spec sheet for this amplifier, and let's look at a couple specs here. First of all, from 20 to 20 kilohertz, you should have about 0.1% THD at maximum rated power. Okay, so what that means is at 110 watts, it should only be 0.1% distortion maximum, okay, at rated power. It should be that or lower. That is definitely not what we're getting from either channel. One channel seems to be a little better than the other, but we are certainly exceeding this at least somewhat when we hit that 110 watts per channel. And if we look at, they actually were kind enough to give us the actual distortion chart, and you can see we should be in that 0.01% range, below that, below 0.01%, all the way from 1 kilohertz, 20 hertz, and 20 kilohertz. You can see they track all the way up. This is a logarithmic chart, all the way up until you're getting very close to your rated power. And even at 100 watts, you can see it just starts to cross that threshold of 0.01. But it doesn't get anywhere near 0.1% until you get through that 110 watt per channel power rating. So this amplifier is not performing up to its standards that it should be. Now, the preamp section is only rated to have an output voltage of 2 volts maximum. Now, open circuit, high impedance, this can go way, they have this circuit designed very well. It can output more than 4 volts before it even gets close to clipping. So I'm going to do a worst case scenario, and we're going to have an output of 2 volts RMS. You set the input so that the output gives us that through the preamp section. And we're going to look once again at our distortion and see what the distortion in the preamp section is. Okay, we have the output of the preamp set. And don't worry about this. This is wrong because I'm not, we're not looking at the speaker outputs. this is the number we want to look at, 2.02 volts. So it's 2 volts RMS. So this should be ample power or ample voltage level to drive the amplifier to full power, is what it's saying, okay? Or at least to drive it to where the specs are measured. And let's go over and look at our THD. And it would help if I back the camera off a little bit. There we go. And you can see that's a pretty respectable number. This is additive. There's always going to be some internal distortion from noise and things in the meter. It's very hard to read very, very, very low THDs, but this is a pretty good meter at doing that. And if I move to the other channel, okay, and I input and I look at the output of that, it is very similar. You can see. So again, and by the way, the preamp is tracking very closely, because the first channel was 2.01 volts with that same input, and this one is 1.99 volts. So the gain of the preamp is very symmetrical between the two channels. So we know our power amplifier section, the two channels perform a little bit different with distortion, and they both exceed what they should be showing at rated power. Okay, before we close out this video, I wanted to do one last test, because I wanted to see if we could use the spectrum analyzer function of this MDO scope to look at audio frequency spectrum. And I still think that you can, but I have tried every setting in this entire unit to try to get this to work, but you can see that I'm seeing every single harmonic. That's not correct. It doesn't correlate with any of my other test equipment. This is a bogus reading, and it has something to do with a setting that I have on the scope. This is where it comes in that I'm not familiar with this piece of test equipment yet, and I'm going to have to read the instructions a little more carefully to see what I'm doing wrong. But unfortunately, I'm not going to be able to show you. What I was hoping we could do is look at the spectrum on this and compare it to what the spectrum looks like on the HP 3580. The 3580 is an analog spectrum analyzer. This is digital. And I think some of the sample settings and things, if they're not correct, it'll do things like this. And I think that's my problem. I just haven't been able to figure it out. I would like to also switch this over to the FFT, which I would expect it will work, but let's do that real quick. And I don't know if you could see, because it's a little bit dark with the camera, but because of my lighting here, let me turn off another light here, because I'm getting all kind of reflection off this screen. There, how's that? You can see the red trace is the FFT, and it is working very well. So FFT is good, and you can see this. What is this? Probably the third or fourth harmonic. There's your fundamental 1 kilohertz, and I think it's 1 kilohertz per division the way it's set. So it's 2, 3, 4 kilohertz. So that would be the fourth harmonic. There's a little bit there, and you can see the second harmonic. There's just a tiny little bit down there. But there is where your distortion's coming from. And then out here, what is that? Fifth, sixth, seventh, eighth, ninth harmonic. So there's definitely something going on there, I guess, a little bit. Again, that's very low if you look at the dB scale. But nevertheless, we're seeing it. So, well, no, that is high, I guess. They're not that far apart. Very interesting, but I guess the point that I'm making is we can look at the FFT and everything seems to work, but I cannot get the spectrum analyzer to work in the audio spectrum. So I need to do a little more reading on this, but general consensus, I'm pretty happy with what all I was able to do with this MDO scope. So there's some tests that we did, and like I said, it just playing around here, experimenting. I hope it was interesting to you, and I hope this video will be helpful at least a little bit. With some of the tests. There's so many different tests you can do on an amplifier, and each one has its own things that it can reveal about how an amplifier is performing. But I'm going to post this video, and I think, as you can only imagine, our next video we're going to try to see if we can do things to this amplifier to improve those numbers. And invariably, because I'm so busy at work, there's going to be a delay, and I will forget all of this. I'll have to try to go back maybe and watch the video again or whatever after I post it, to see what it was, and we'll try to compare after we work on this. So I hope you enjoyed it. I hope I didn't confuse you more, and maybe I confused myself. I don't know. But hey, we're having fun, right? That's what this is about. At least for me it is. So until then, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again soon, where hopefully this Rotel will be either performing as good or better than it did when it was new when we're done. Until then, take care. Bye-bye.